Welcome, everybody. It's my pleasure to introduce Killian Meehan, who today will be telling us about comparative stability of two zigzag bottleneck distances.
Well, thanks again. As Shu said, thanks for running this. Even though the current state of the world makes it difficult to meet in person, this is really great that we can do this. Thanks for everyone tuning in from all the various time zones. This is the first time I've had the chance to double date the presentation I'm giving. So that's pretty fun. Yeah, so I'm Killian. This is all collaborative work with David Meyer of Smith College. This is Kyoto University Institute of Advanced Study, the same institution as Shu, and in fact, we're in the same laboratory, which unfortunately in recent times doesn't mean we get to see each other much, but we are only some 20 minutes away in reality. All right, and this is comparative stability of two zigzag bottleneck distances, even though the recent abstract mentioned a third. That will come up briefly at the end. Okay, so what are we looking at? You got persistence. Most persistence is, most people's first exposure to persistence is one-dimensional. You have some filtration of objects that get more and more complicated. Homology gets applied, and you wind up having this vector space object indexed over the real number line, or that can be discretized to poset, a totally ordered finite poset, which turns out to be equivalent to a quiver of AN type that is equioriented. So I'm sort of coming at this from the quiver theory and the algebraic topology sides at the same time. Zigzag persistence refers to this similar straight line structure, but all the orientations of the arrows are arbitrary. And this is, well, I guess my first question with this was, why might this be interesting? And then far after I submitted this talk and came up with the abstracts for it, I started working on a project where this actually became really relevant. So what I have across the top are three structures, but they are dual indexed. They are dual indexed, and true two-dimensional persistent homology is just, it's a goal, but there's a lot of qualitatively very high walls to climb over to get there. But I have this sort of chain carved through my 2 dimensions of parameters, and I want to trace this chain. But because I'm going by 2 dimensions, even if in each dimension there's some sort of including relationship, I'm sort of taking an off-diagonal progression, which means that these objects do not inherently relate to each other in any simple way. Their intersections, however, are a very easy way to relate them. So this is the most, maybe this was proposed even in the initial zigzag persistence paper as the most basic way you could wind up encountering this. You have a bunch of non-comparable objects, but their intersections or their unions allow you to create some sort of including maps going upwards back into them. And so that's where you get this zigzag structure coming from. Okay, the first thing you do when you're looking at some kind of persistence is you want to talk about comparing the final results, the persistence modules. By and large, the most general one is the interleaving distance. This is completely categorically defined over any poset structure with values in any kind of category. It's the best in the sense that it represents shift isomorphism. If you have 2 persistence modules, they're not the same, but what kind of shift upward or forward along the poset would allow them to then be isomorphic across the board? That's the best I can do for intuitively describing the interleaving distance, but it just does this rather impeccably. Problem is, it's awful in most practical ways. Dealing with this in an applied problem and even dealing with it theoretically, it just has a lot of difficulties. So a really popular alternative has been this idea of a bottleneck distance. And I say a bottleneck distance because bottleneck distances always come from some other distance. What you do is you have your persistence modules, and if they decompose nicely, and all the things that we're going to be looking at do, 1D persistence modules and zigzag persistence modules both decompose into interval type objects. Then you start with your persistence modules, decompose them, pair up the members of those two decompositions, take the pairwise distances between everything you paired, but now those objects are fundamentally very, very, well, much simpler than the ones you started with. So talking about a distance between these two very simple objects is much easier than the entire summed objects were. So you compare them pairwise, and if they weren't all matched up, you just compare them with 0, and you take the max over all that stuff and say, okay, that's my bottleneck distance. And again, this is an induced thing because you need to use the original distance to compare things pairwise. This is wonderful, but is it remotely okay to do this? This seems like qualitatively things might just radically change. If you decompose everything and then pair them all up, your distance might just become massively larger than the one you started with and even unbounded. So when you do this sort of thing, the first question is stability. Is it okay to use the bottleneck version of whatever you started with? As it turns out, for real index persistence modules, and the interleaving distance in particular, its induced bottleneck distance is very, very okay to use because it is in fact equal. It is isometric to the distance you started with. You lose nothing by being able to decompose everything, deal with them all pairwise, and just have a computationally and intuitively much easier problem to approach. This has a bit of a long history of its progressive developments, so most of those are referenced here. Great, we would love to do something like that with zigzag persistence modules, and we're going to, after we just address one small thing, which is that if you don't do anything special, the interleaving distance on any sort of zigzag, pure zigzag structure is completely trivial. There is no interleavings, if anyone knows the background of this, are built off of translations. And there are no non-trivial translations on a purely zigzag poset. So this is not a qualitative comment, this is a quantitative one. There's just almost nothing to do if you take the exact definition of interleaving distance on a zigzag poset, which of course people realized right away. And so what should we do instead? Enter the block distance, as discussed by Botnan and Lesnick. So there's a lot of pictures here. You take this blue poset here and call this your zigzag poset. So one thing to mention, to interrupt myself briefly, is that the block distance works for pure zigzag orientation. Every arrow alternates, not fully arbitrary, maybe a couple chains of leftward or rightward arrows. So you represent your zigzag structure like this, and you sort of embed it in this solar wind, I guess, that I'm drawing here in the real plane. So increasing direction is this diagonal, which means all arrows are pointing from these points upward to the ones along the diagonal. So if you take this poset and you just, this poset can represent all zigzag persistence modules that you would ever be interested in. You embed this into R2. You also, or you embed it, you view this as a subset of the real plane. There's a lot of categorical ways to very carefully talk about posets, embedding into other posets. Pretend that's all being spoken very, very eloquently, or just go read the original paper. You also look at this upper half plane as well. And what you wind up doing to turn zigzag persistence modules into real plane persistence modules is a con extension by colimit. You take any point up here, you take some particular zigzag persistence module here, then you take any point in the real plane, project down and take the induced sub persistence module by this sort of triangle. And the value at U is the co-limit of this structure in incredible brevity. What this manifests as in all various types of indecomposable zigzag modules, let's just look at those, are the four following types. So if you have an indecomposable zigzag module that its left endpoint is low and its right endpoint is high, you get some infinite vertical strip. Opposite, infinite horizontal strip. Low, low gives you this finite region. High, high gives you this infinite region. So we have the block distance. We're going to call all, so what Botnan and Lesnick did is they actually said, we don't need to reduce this to a discussion of zigzag modules. Once we projected the zigzag modules into this form, let's just make a general result on all modules of that type in R2. So block modules are any 2D persistence modules that decompose into modules of those four types listed on the previous screen. All zigzag modules decompose themselves, so they can all be projected as sums of blocks, so it all works out. And their initial result plus a follow-up, the dates look odd because this was first mentioned in a preprint, but this is the publication date, with Bierkovic, confirmed that in fact this distance, this projection by con extension followed by interleaving distance, also is isometric. The block distance and its induced bottleneck distance are equal. So that's great. What does it look like in practice? Well, now we can just view the block distance as a bottleneck distance in all ways because we just showed that they're equal. So it is its own bottleneck distance. So we have these four types, this sort of open, closed, closed, open, 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 closed, closed. So what does this block distance do on indecomposables? Within the same type, distance is L infinity. Compared to interval type modules, because all these blocks can be represented in an interval format, just take the max of the difference of the endpoints. That's all you got to do. You cannot directly compare different types. One argument for this is that if you just take any two qualitatively different shapes from here, their interleaving distance winds up being, if you want to compare them directly, infinite. So you cannot compare different types, which means that, for example, if you want to take an open-closed interval and compare it with a closed-open interval, your comparison winds up being matching both of them with 0. You just cannot compare them directly. Distance to 0 itself is mostly a simple scaling with interval length, except for these closed guys. Since they are an infinite region in both dimensions, the interleaving distance of this thing to 0 is infinite. That's maybe the kind of starkest, strangest property of the block distance. So what did we do? What did we do? Well, we were proposed with some inspiration from actually my current boss and one of our other laboratory members before they were my boss and fellow laboratory member. Yoshiwaki, Hiraoka, and Emerson Escolar did a paper on stability with ladder diagrams using some quiver theory to apply to persistence. So with that as sort of our inspiration, my friend David and I looked at this. You get a quiver, never mind, you don't have to think of it as a quiver if you don't even want to deal with that. A zigzag poset, it's got this special algebraic object called the Auslander-Reiten quiver of that structure. It takes all the algebraic objects, all the indecomposables over that thing, and arranges them algebraically. It's incredibly sensitive to orientation. Here's just a length 8, totally ordered poset, and its Auslander-Reiten quiver. Split it in half so the arrows go left here and right from here, things get weird. Make it pure zigzag, things get very weird. How do you make this into a distance? Graph distance. So what we're about to define is fundamentally a bottleneck distance from the outset. It has no non-bottleneck form. All we do is reduce things to indecomposables and then pair up and measure. So the distance between two indecomposables in this bottleneck distance we propose is going to be the graph distance within the Auslander-Reiten quiver. And we're going to weight that distance by these edges here, where if you skip a lot along any edge, if you go from a very small module to a very large module, the difference in dimension of these modules is going to be factored in. Distance to 0 is going to be distance to the nearest simple plus 1. So you can only escape the Auslander-Reiten quiver through the smallest indecomposables. Okay, a couple really weirdly convenient things happen here. The Auslander-Reiten quiver for pure zigzag orientation perfectly partitions by type mentioned back in the block distance definition. I'm going to have to hurry this along here. But that's, so you got this perfect partitioning. Distance to 0 is pretty easy. On the right and left-hand side, these corners are all simple, so you can always get out very easily. On the top and bottom, though, that is not the case for pure zigzag. So you wind up with this kind of weird problem where all these highlighted guys, their distance to 0 requires them to go uphill, in a sense. They have to first go to a larger module and then count down to some simple to get out. In pure zigzag, this actually becomes incredibly extreme to the point where you can have, there's always a candidate module for this with dimension 2, and its root outward is takes a full distance of about the size of the poset itself. This felt qualitatively very undesirable to us, so we realized there was a kind of interesting way to fix this. Here's a comparison of the chopped off top halves of the Auslander-Reiten quiver for the following two posets. In pure zigzag, this whole highlighted region has to go uphill to get out, and thus has a distance to 0 much larger than its actual size. 10, 11 right here is a great example. It's a very, very small interval, but its distance out of the poset is massive. Refining, thickening the poset here with just an extra set of points between every max and min completely demolishes that problem. The structure is qualitatively the same. It's still zigzag, but the algebraic change of these extra points removes this huge region that seems to counter a lot of what we would like this distance to intuitively measure. So we got that fixed. There's a new problem. Unlike the block distance, you can compare different types directly, and their distances are finite. However, these distances scale with the left and right endpoints of your finite zigzag structure that you chose. Since that choice is fundamentally arbitrary, a distance depending on that also really did not seem desirable. So here winds up being the full progression from what we started with to where we end. You start with a zigzag, just a zigzag poset. You first embellish by adding these points in the middle. You then start keeping the zigzag structure identical. You start stacking on the left and right side, and you take a limit as these go out to infinity, so you do not have to deal with choosing some finite limited zigzag poset. When you embed these module categories, you wind up getting an Auslander-Reiten quiver of these guys getting spread out like this. Then you cut these regions, and when you add those bits onto the end and take a limit as that goes off to infinity, these 4 type regions are separated to the point where their graph distance approaches infinity. So now you no longer can compare them, which is better than being able to compare them, but their comparison relies on something fundamentally arbitrary with no relevance to the problem you're working on. So after these 2 adjustments to our distance, we wound up, the goal initially was, because we have no internal stability result, we have no non-bottleneck and bottleneck forms to compare, we figured the best thing to do was to compare it to this prominent zigzag distance in the literature. And the similarities, despite coming from these completely different sources, wind up being almost eerie. Just by stylistic choice, I guess. Within type, the block distance does an L infinity type distance, and ours, since it's a graph distance, is L1 type. You add the endpoint differences instead of taking a max. Across type cannot, across type cannot. Distance to 0, usually a factor of 1/2 or 1/4 for interval length. Ours is a factor of 1, except for a few outliers. This is just like a very, very limited case. Whereas block distance has these infinite type distance to 0 guys, which allows us to say, if you have two persistence modules, zigzag persistence modules with finite block distance, I have to qualify that, then the block distance actually bounds the Auslander-Reiten distance with a 2 below and a 16 above. Qualitatively, even though there's a lot of infinities going on, if you can dodge that one thing, they bound each other reasonably close, which we were really surprised to find. And then my final comment, just because this talk really would not be complete without it, my boss and another of my fellow laboratory members, we had a lot of conversations about this when I was finishing this paper and they were finishing theirs. They take an entirely different approach to the zigzag persistence module measuring by going at it with derived categories, which is it's a fascinating read. They prove their own internal stability result. It turns out to be another perfect isometry. The initial distance is equal to its bottleneck self. The interesting thing is that unlike the two distances I just mentioned before, this one winds up with 2 incomparable regions instead of 4. And the reasons you get there and the algebraic and categorical argument for it is, I think that's really interesting. So I encourage you to check that out. That's all. Thank you.
Fantastic. Thanks so much. So before we get to questions, please everybody go ahead and unmute yourselves, and then let's clap, and then please mute yourself again. Questions for Killian? So Killian, I had a question first about the definition of the block distance. So when you're taking this co-limit to get to that point U, on the original zigzag diagram in blue underneath, you have a vector space at each vertex. You have a diagram of vector spaces, and so you sort of populate that point at U when you take this co-limit, or sorry, this con extension. You populate that point U with a vector space as well.
So let's say the way I drew this, let's say that the gray is just it's the whole poset, but yeah, this one, the blue is the support of this interval zigzag module. So for every point U, you project down and take the sub poset that you cut out, as well as the original persistence module as restricted to that sub poset. Take the co-limit of that structure. So all you wind up with are base field or 0. And in this case, the U right here, the co-limit, the poset is full, more or less, right? The restricted poset and the restricted module have, like, the support is the whole thing. Co-limit turns out to be 1. If U rises up higher than this point here or leftward of this point here, you introduce points, and you can chase the diagram very quickly to realize that it kills the entire co-limit. I believe it's co-limit. I think I checked when I was making these. You can make this all dual if you want to, but I believe it's co-limit.
Sure.
And so that's where these shapes follow from. You get this thing where it's like, because it's co-limit, it's a matter of if you have a low point, like here you can see, if the support of the module covers this point but not this point, and you include both of these, if you include both of these in your like restricted poset, that's the sort of thing that kills the co-limit. So you cannot have any point above here, or even if you include these, this little comparison right here is what reduces the co-limit to 0. And something like that works in all 4 cases.
Mm-hmm.
Um,
Thank
yeah.
you. Further questions? Killian, are there still sort of a lot of outstanding open questions or conjectures relating these various distances?
To me, the open questions are, well, I guess what I thought was most interesting when I was looking into this was that even though you wind up with this zigzag structure where, I don't know, in my mind, you can index a zigzag structure from left to right, but in a poset sense, that doesn't really fit, right? There's no reason that this point over here, it has no relation to this point over here if you go up and down a few times. And yet most of these distances through all these various algebraic approaches wind up with something like L infinity, in our case L1, which again qualitatively is only different by a factor of 2 at most. So you have that a really good way to measure distances between these things winds up being just something I wouldn't really have expected. But zigzag is very weird like that. Like you can't, as I said near the beginning, you can't just apply the interleaving distance outright. It does nothing. If you let yourself treat it just purely as a poset where you say these points are non-comparable, so they have no relationship whatsoever, the distance between these points in a left to right sequential way shouldn't matter, well then your problem almost reduces to triviality, so you kind of have to let it back in. I think it's yeah, well, I'm about to wind up using these in an applied project, which I frankly wasn't sure when I was working on this with David that I would ever say that, but now I'm very interested to see how each of them kind of pan out when I look at this sort of thing. So I think the answer is that it's very open. They're qualitatively very open, even like how is there, what kind of ways are there to think of this stuff?
Sure.
And
Yeah,
with anything above one-dimensional persistence, that's kind of my feeling. It's so weird and so difficult, and there's so many negative results made about standard approaches that if you have an interesting way to view this stuff that develops into some mathematical, some kind of foundation, then I think that's just really interesting in and of itself.
Mm-hmm. Fantastic. Last chance. Any more questions? Well, if not, thank you, Killian, for a beautiful talk.
Thank you.